So what are we looking at here? It's a 7,000 pound max gross takeoff weight, all electric aircraft. It's got just over 500 horsepower in the tail of an all electric motor. That motor is right next to Steve here. It's a dual redundant motor. So there's actually two motors inside there pushing that singular prop. There's 5 batteries in the belly there, and it's about 4 times as much energy as like a Tesla Model 3. So it's a boatload of energy. There's 2,800 pounds of batteries in that. And this class aircraft, not this particular one, everybody asks these big questions. How far does it fly? 336 nautical miles is the longest we've demonstrated in this class of aircraft for about 3 hours in the air. So it's got some meaningful endurance. And the reason I bring that up is that what we were seeking with electric aviation is to get to the point we could cross the threshold of doing a commercially viable mission. And a commercially viable mission means that you envelope a large extent of a particular customer's missions with all the reserves at the payload and the speed that you anticipate. And we did that as an industry a couple of years ago with Amazon, UPS, FedEx, all the feeder fleets that they do those flights in, and a bunch of medical flights. So the aircraft was designed specifically to make that particular range, that particular payload, and that sets the scale of the aircraft. The neat thing is, as they get bigger, they'll go a little faster, and they'll have longer range, and it'll be compounding because batteries are continuously increasing their energy density. So naturally, we're pretty excited about the future and the prospects of electric aviation, starting with this. This is one of 2 variants. This is a conventional takeoff and landing aircraft. The other variant has 4 lift propellers on it. That's an aircraft that takes off and lands like a helicopter and flies like an airplane. So that's a general overview of the airplane.
My name's Chris Caputo. I oversee flight operations at Beta Technologies. I had the very fortunate opportunity to meet this gentleman here about 6 years ago when Beta had about 25 people in the company. And Kyle said, we should teach everybody here how to fly, all the engineers. And, with that, we've developed this culture at Team Beta where we have a much more informed engineering product. We've got a really rad R&D flight test crew. Where's Daniel Cash Dollar? He's one of the flight test engineers that leads at National Test Pilot School, graduate out of Mojave, that is really getting into all the engineering and handling characteristics of this aircraft. But then we've got this other flight school that teaches people how to fly. And gets people really, really, passionate and behind what we're here at Oshkosh for. Just because we all love aviation and want to do it super safely and super reliably. When you bring those 2 together, we've got this group of aviators that just got checked out in this aircraft that are flying it not only all over the United States of America, but aircraft number 214 Bravo Tango, literally just took off today from Hamburg, Germany, and landed up in Denmark, and it's on its way up to Norway. That aircraft's been flying all through Ireland, through England, flew every day in the Paris Air Show, made it all the way through Germany, Luxembourg, and it's been doing customer demonstrations throughout Europe. And I think what it goes back to this guy's vision about, we're not going to show up at an air show. We're not going to show up at an airport or with a customer on a demonstration without having flown the aircraft there. And we've got this group of really, really talented, passionate people that are collecting not only all the really informed engineering decisions that our team of engineers back home are doing to design this aircraft, but all the operational data that is being collected from having these aircraft out in the wild flying every single day. We're flying them, we're charging them on our own operational network, on shore power that exists at current hangars. And I gotta say, having spent 30 plus years in the military flying A-10s, F-16s, a bunch of time at Delta Airlines flying 7.5, 7.6s, there's just something super satisfying and unique about this aircraft. You almost become one with the plane. It is so quiet in the cockpit, you can actually feel the airflow over the cockpit, over the wings, and it is just such a simple, artful design, and the avionics inside are just very, very thoughtfully well laid out. It's just a joy for a pilot to fly.
Yeah, just as like a guy who flies a lot of things and I'm not a professional, I just get to jump into different aircraft. This airplane looks very unique and different, but I was super impressed with how easily it flew. And I guess it's important to know it's a fly-by-wire system. So in the current setup is direct law, and if you know much about how that stuff works, it means you tell it to do something, it's like, okay, no help. And normal law is what will ultimately be implemented to kind of help make it easier to fly. But even in direct law, where you're potentially at a risk of getting into a pilot-induced oscillation scenario if you start to like get behind it or over control it, I didn't really have too much trouble. I learned in the sim for, I guess I had one session, and then jumped into the real airplane and they let me land it. You guys are a little crazy, but because the other problem is, I guess, the nature of the setup is that the controls aren't connected physically, and what will happen is if that one pilot tries, I guess the briefing was, if we have a bird in front of us and you go left and I go right, the airplane will split the difference and go straight. So the briefing was, you have control until I say I have control, and then you have to like let go. So for landing, it's all you or it's not, right? So it was a little stressful. I mean, this is one of how many airframes at the time when I was flying it? Two. So I didn't want to break it. And yeah, it was a kind of gusty day, and I landed it twice, and it really performed beautifully. I think the challenge that I had was that it glided too well. I'm used to flying RV-14, which is what I fly mostly. I also fly a T6. Neither of those glide exceptionally well. So you don't want to set yourself up tight. Is it a 16-to-1 in this configuration? So that's like a huge glide ratio compared to what I'm used to. And you don't really, I mean, it's ultimately designed to be a VTOL airframe, so it doesn't have flaps. You have a drag region with the engine that you can use to slow yourself down. That's kind of it for drag. So you really have to manage the energy well, and it was not something I expected that an airframe that's fundamentally designed to be VTOL flies so beautifully in the CTOL configuration. It does take a little bit more runway for takeoff and landing, obviously, because of the speed that you're looking at. Ultimately, in a VTOL configuration, I think it's going to be pretty cool to see how versatile it's going to ultimately be. But as a pilot that didn't have a lot of experience with wacky stuff, I did not have a hard time transitioning into it.
In any aviation, specifically in electric aviation, there are 4 primary variables that allow you to carry a lot of weight and go a long distance. That's what we're trying to do with airplanes. And it's you make it slippery, high lift over drag ratio. You have a low structural weight fraction. That means all the stuff that's not carrying energy or carrying stuff doesn't weigh a lot. The energy that you're carrying has a high energy density, so for every pound of energy you're carrying, you carry a lot of energy. That's the specific energy density of the battery. And the one that a lot of people forget about is the propulsive efficiency. How efficiently you can take that precious energy in your batteries and convert it to propulsion. And that's where we've really started to differentiate ourselves. We're going to get you a new hat from that Joby hat. Can we get this gentleman a new hat? I'm just kidding. This is where we tend to differentiate ourselves. And people ask all the time, what is the reason for the 5-bladed pusher propeller versus thrust vectoring? And it comes down to propulsive efficiency. It's the way in which you can convert that energy into propulsion, whether you're trying to hover and you have a high figure of merit, or push the thing through the air with a high efficiency. And one of the fascinating things, you guys are all airplane nerds because you're standing here. One of the things that blows my mind every time you look at an airplane is all the energy put into that airplane moving through goes through those 5 blades. And if you look at that thing, it's not a lot. All the energy that you're pushing through goes on that entire airframe. So the aerodynamics of those blades is as important as the entire airframe. And proportionally, I don't know, it's a 100-to-1, 200-to-1 ratio. That means that every little airfoil and advance ratio and angle of attack is so important on that propulsion in order to make high propulsive efficiency and put the thing through the air efficiently. So those are the 4 primary parameters. And then Steve hit on something really important. Then you have a design philosophy after understanding the physics. And the design philosophy for us is simplicity. That's it. Just simplicity. And in the case of Hilario, Former head of certification, all the FAA right there. Listen to this. We better get this right. The design simplicity is really important. You notice all the batteries are in the belly. And as Steve was describing, in direct law, the aircraft is very stable, has good stability coefficients. And that means that the aircraft's behavior, like upon stall or upon correction or overcorrection, you end up coming back to neutral in general, or you stall and the nose drops nicely, doesn't depart controlled flight. We decided that even though we have a fly-by-wire system, we were going to make an inherently stable aircraft, so it needed no augmentation on top of the fly-by-wire system, which ironically grossly simplifies the software necessary to control the plane. In fact, it goes to direct law, proportional law. You put in this much, it puts out that much. And so these types of design philosophies around simplicity and a respect to the first principle physics is all that we had to provide to guidance to the teams that then broke off and engineered the various elements of the airplane. So that's all I got on the design.
Just one more thing about redundancy. A lot of people ask me these questions. I'm not an engineer, but I understand enough about it, having worked with these guys. And if you look at the control surfaces on this airplane, there's a lot of them. And essentially what we're looking at is split, separate systems, so that if you lose a whole half of the airplane in terms of the electrical system running it, you still have control authority, which is pretty cool how much they've thought that through. And it's the same with the engine, and you get arguing with people about motors versus engines. I came into the world of like flying airplanes, and people talk about the motor, and it's like, it's not a motor. That drives me crazy when people describe an ICE engine as a motor, right? Your starter motor is a motor, but that is actually an engine. And I learned that as I started working with them here, and it's pretty neat how it functions. It's built on multiple components, 2 of which are motors in each one. So right there is a redundant aspect to it. But I think what's cool about it is that the failure mode, if you were to compare the motors in this airplane to pistons in an ICE engine, losing a piston in an ICE engine probably means you're shedding parts and you're sending metal through the system, and you're probably looking at a complete engine failure imminently. Whereas something like this, if you lose a motor, it's going to just not be part of the system anymore, but it's not going to drag. Like, I guess maybe Pooter can speak to the actual redundancy and safety of that aspect. So yeah, you're going to lose power, but you're not going to lose the engine. And that's kind of been interesting. When I publish videos about this stuff, people start arguing in the comments about motors versus engines, and it's like, it's an engine. That's how it's going to get defined. That's how it's going to get certified, I guess, right? And it's important to understand the redundancy that you're looking at because of the systems involved. There's a lot more to the engine than just a couple motors in there, but it's a lot of redundancy.
You know, Flight Chops, you bring up a great point. The overall simplicity of the design of the aircraft, and we go back to start talking about flying the aircraft and why it is so much fun to fly. You know, you have all these advanced new aircraft on the market that are very technologically advanced, but they have complicated systems. They have complicated avionics. How we partnered with Garmin and the customized synoptics that are in the aircraft make it very, very intuitive to the pilot. Early warning, crew alerting systems, just incredible insight into the soul of the aircraft through the avionics provides really good intuition to the pilot. And what it makes it really enjoyable, because now you can focus on the things that matter, about controlling the plane, about not missing an altitude or a radio call or turning to a heading, and doing that really, really safely. And it almost makes, flying fun again. For me at Delta Airlines, when you were just flying from point A to point B and turning the autopilot on and not actually flying the aircraft. You're one with the machine. It's very, very simple to understand. And if you start looking at the redundancy baked into the aircraft, all electric airplane, lithium ion batteries, an electric engine, and folks are really focused on that from a redundancy standpoint. But from a pilot perspective, what I'm most concerned about is the low voltage system and the fly-by-wire system and how to control the plane. And the fact that you kind of touched on it, not only is it electrically redundant, it's geographically redundant, and it's mechanically redundant. So the level of redundancy throughout the low voltage and the fly-by-wire system to be able to actually control the plane is really, really easy to understand for a pilot.
Yeah, just to explain the engineering behind what Chris is describing, there are 3 times redundant bare metal computers that we actually make at Beta inside the nose of that aircraft. They're fed by 3 different power systems, 2 primary and 1 backup. But Steve brought up a really interesting thing. If you look right over Ed's head there on the control surfaces, you'll notice that the outboard control surface is just a little bit narrow, a little bit shorter than the inboard control surface, because the rotational moment on that is a little shorter, so you need to make up for it by a larger control surface. And that makes it so that after you do all the electrical voting and all the redundancy, you get what I call aerodynamic voting at the end, where if you have one failure of those 3 and it's a hard over, then it's always equally outvoted by the other control surfaces. So after all of the electrical fanciness, there's 10 control surfaces on this airplane that all have equal control authority, either in roll, pitch, or yaw, relative to their counterparts. So there's I think a thoughtful architecture, and what Pooter described as this geographic redundancy. Every control line going to that servo or that motor or that battery takes a different path through the airframe. So there's no point in the airframe where you could put a bullet through it, a bird through it, or have a fire, and you would lose control of the airplane. So that geo-redundancy allows you to have this total system level redundancy on a when you have any particular failure in the airplane, which then gives it the path towards certification. I'm actually going to make a cool announcement, which maybe you guys heard at the press conference this morning, but that prop was type certified on last Friday. Yes, and it's part of our certification strategy, which is we're going to go prop, engine, airplane, VTOL, and then larger airplane, and every one of them, they're overlapped quite a bit. And the neat thing about certifying that prop, is those who have gone through certification programs before, is that prop collected the data on that motor to get certified, and the endurance testing, the ingestion testing, the halt testing, all that type of stuff had to be done on the motor that it intended to be certified on. So it gives us a bunch of confidence. We know how to get through the motor cert, and then we go through the airplane cert, which is already quite a ways down the road. So that was a big win for the Beta team on Friday. You were flying a near certified prop.
Well, I want to ask Mike a question. We not only did Kyle, kind of stalk Flight Chops at previous Oshkosh, but we also got introduced to Flight Chops from where's Jerry, our videographer, that just where is he? Okay, he's with the baby. That really kind of stalked Flight Chops of coming to help tell the story about this new electric aviation company and this new product on the market, and showing that there's actual substance behind this company and this machine that we're designing and building. But I wanted to ask you, one of the new and novel pieces of this is the rudder in the hand, and throughout your training with us and all the flying you've done, can you talk to the team of aviators here of your experience with rudder in the hand?
Yeah, that's a good point. That's one of the things that immediately I kind of had a little bit of pushback on just looking at it, right? It's like, okay, as a simmer, when I had my flight sim equipment at home, I was less excited to get rotor pedals and take that twist joystick out of the equation to set up a flight sim as close to what I really fly as possible and get the best rotor pedals that move, not just still. I want to really feel like an airplane. So getting into this, I felt like initially, before actually flying it, like that it was going back to that world of like that twisting stick that I didn't love. And I guess I was stressed about the fact that the pedals are brakes only. So as a tailwheel pilot, my concern was I'm going to be on the roll touching down at what is this, 65 or 70 when you touch down, a 6,000 pound airplane. I'm going to hit the rudder and blow a tire or something, right? Like I'm going to leave a ton of rubber behind. So that was my concern, and I did do it in the sim on my first shot because we got put in a big crosswind, and we briefed it, feet are on the floor. But as soon as I felt like I needed it, I did do it, and I was like, oh. So anyway, it was good to do it in the sim and then get in the real airplane. And then we went and flew, we did slips and stuff, and I could really feel how that was working to slip it. And when I really landed it, it didn't happen. And again, I really had limited exposure. So I think, yes, it's going to be a transition for pilots that want pedals. But I guess you guys can speak to the engineering reasoning why you're going that way. I think I understand it from a simplicity perspective. There's a lot that would have to happen to get rudder cables or whatever, moving pedals, more complexity that we're trying to minimize for the sake of safety and redundancy. So yeah, it's a new way to fly an airplane, or I guess an old way to fly for some simmers. There goes is that a B-52? Anyway, yeah, so flying with your hand only was interesting, but it wasn't as big of a challenge as I expected, and it went pretty smoothly.
So I'll go back, way back in time. So my senior thesis in college was Beta Air. And the basic premise was there's a better way to fly an airplane. And to use the biokinematics of your body to an advantage versus a disadvantage. And I know that you love rudder pedals, but it's totally unnatural to go like this and then switch and catch the adverse yaw. It's a dance that we all learn to do. But the reality is if you take your hand and you twist it outboard, it turns a little bit. And you twist it inboard, it turns a little bit. And if you map that, then a natural coordinated turn should just go like this, right? You're going to twist and turn at the same time. And that's the simple premise of it. Make it more like your body and less at the convenience of the machine. If we think about why we had rudder pedals, because way back when we said, okay, a way to move the airplane in yaw was to move something that's had a vertical axis. A good way to translate that motion was to move our feet back and forth through a pulley and probably a bell crank back to a whatever and turn that back and forth with some cables. Is at the convenience of the machine. And the interesting test that I did a long time ago before this is I put my son in a little aerobatic RV-8 and I was like, okay, look, I'm not going to give any instructions. We're going to point right at the mountain and start flying at the mountain. And you know what they do to go up? They lean forward when they have no training whatsoever. They pull the stick forward with them. Like, or if you take somebody and you say, let's go taxi this plane, they'll turn this the wrong way all the time. It's a learned behavior is my point. To pull back, lean back, and you go into a hill. If you ride a bike into a hill, you lean into it to go up the hill, and you lean down to go down. It's the opposite in an airplane, right? We learn this stuff. That stick resolves one dimension of it, and we have a dream, or I have a dream anyway, to resolve all the dimensions of flight into a full pressure-based control system that all you're really doing is thinking where the plane's going to go. One other thing I want to mention. That goes out to the system level design. And everybody's heard of adverse yaw, where the upward facing aileron drags a little bit and you have to add that. So this airplane is minimized for adverse yaw so that this works beautifully, right? And you do that by the natural incidence and the natural force that's already on those ailerons. So it actually will come up a little bit before it has any downward effect. So the inboard on the turn actually has more effect, and it has proverse yaw while you're coming around. So you have to think system level in order to implement this type of thing.
And I guess a good point was that it just didn't need that much rudder. I think that's
because of that design.
Yeah, so that was what I was fighting with, was realizing, oh, even in a crosswind, it didn't need what I thought it might. So I was overthinking it, clearly. But it is nice that when you want to slip it, it actually does a pretty good slip, and it will start to really come down. So the rudder is effective, it's just that it wasn't as necessary in normal ops as I thought it might be, so the twisting wasn't that big of a hurdle to get over.
So can you do a power off 180 and land without power, just 180?
It can do a power off 360 and land without power. Yeah, it glides really, really well. You know, going back to what Flight Chop said early on about the glide ratio, and then when Kyle's vision about teaching our engineers how to fly and have more informed engineering decisions. You know, early on when we started doing some IMC testing and getting on an ILS glide path or an RNAV glide path, you know, we put the airplane in idle, and there's no drag devices on the plane. There's no flaps, there's no spoilers, and the aircraft would just continue on a 3-degree glide path, accelerating down final. And you can imagine if you're in the weather and to control your speed and glide path of trying to slip the plane down final on an ILS in the weather, that's probably not great for spatial disorientation. And you know, you're explaining this as a pilot to a bunch of engineers that, you know, have never flown in their life before, and they're looking at you funny, you know, sideways, and you explain it to engineers that have flown before, and they're like, oh, you know, well, we can, you know, control how that prop spins with ones and zeros, let's generate, an active drag on the propeller, and we are easily able to create a drag device without adding complexity of flaps or spoilers and adding weight to the plane. So the plane glides beautifully. You've got incredible vision out the front, particularly when you're doing a left turn and you're keeping the runway off the left wing, or even out the right side. It's the visibility is amazing, the glide ratio is amazing, and it slips really well, so you can control your glide path.
So have you tried teaching any of these engineers starting with this airplane instead of in a regular airplane?
Yeah, we're not quite there with starting with this airplane. In the sim, yes, there are engineers who really started with this airplane in the sim. We do have a small fleet of electric aircraft that we do train people in that are mirrored by some piston-powered kind of sisters to those aircraft. But we're still seeking the very first pilot who goes from zero to hero in this airplane. I saw some hands go up earlier that are, no, yeah, no. What other questions do we have?
As you move towards serial production and your design philosophy is simplicity and low parts count and design intent, in that process, have you found opportunities to make it even simpler and reduces manufacturing time?
It's a great question. So the question was, as we've moved into production, have we found opportunities to make the aircraft even simpler? It would be really arrogant to think that we got it right on the first try, or the second try, or here, the third try. This is the third electric aircraft that we've designed, and this is the one we've chosen to go into production with. And the answer is absolutely. And the way that I picture it is, you have a problem and you think of wing, tail, motor, couple of control surfaces, and all of a sudden we've got this much complexity. As you solve all the other secondary problems around flying in the weather and whatever, you end up with this much complexity. But as you learn more and more, you condense that simplicity into something called mechatronic devices, where you have something that does multiple functions at the same space and the same time. That motor's full of them. And you simplify, and you asymptotically approach something that is the ultimate minimorum of simplicity. However, if you were to do that forever, you'd never have a business because you never enter production. So you have to strike a line and say, I have a lot of things that I'd love to do, but I got to strike a line today and call this block 1. And then you put things on the shelf. So there's a lot of things on the shelf, to answer your question, that will simplify this aircraft. One of them, there's a lot of fasteners in this aircraft. Get rid of all the fasteners in the aircraft. There's a lot of little caniffler pins and hinges and other such things, but with artful design, you can simplify those down into less and less components. And we want to asymptotically approach that as we get through block 5, 6, 7, and we end up with the simplest aircraft that we possibly can. There's a cool little Jeribou aircraft over there, and it said something engineering and refined simplicity. I was like, they won with that. That's where we want to be.
Thank you.
We got some questions on the live. Someone asked, is the eVTOL version at Oshkosh?
Okay, I can answer that, no. Well, let me just jump in real quick to redeem myself for a second. It was a B-29. I've flown it. And just, there's a lot of people looking at me. But that reminds me that the amount of airplanes these guys have in their fleet is really cool, and there's so many things, from an Antonov to a Beaver to the Pipistrel, and it really speaks to the philosophy of getting everybody on board to fly a lot of things, including helicopters, so they understand vertical flight, but also a steerman, floats. When I saw the fleet that they had there, I was super jealous. I'm like, how can I get a work visa? But anyways, I'm a Canadian. But it is amazing to see the philosophy there, that everybody is excited to fly and invited to fly, encouraged really to fly everything and learn as much as they can about different types of aviation to start working on this novel tech that they're building here. Any more questions from the live? Yeah, you guys want to take the icing question?
Yeah, so this aircraft is an IFR aircraft, so it has inadvertent encounter device, so about 15 minutes. It's got heated angle of attack, heated airspeed probes. We've gone through de-icing testing in this aircraft to the extent necessary to show the accumulation rates allow you to go in and get out. So that's what you need to be to a modern de-iced aircraft. However, if you look closely at the leading edges, they're all removable. And our good friends over here at CAV have a beautiful system with a titanium leading edge that this is perfectly set up for. So in the next blocks of aircraft, we've, like I said before, provisioned for. That's power provisioned, physically provisioned aerodynamically and structurally for a full flight into known icing aircraft.
What aircraft do we have here?
What aircraft do we have here? So we have two versions of our Block 1 aircraft, which is the one right here. It's a passenger version. And then we have a cargo version, which is across the ramp over there that's going to be flying flew in this morning and be flying in the air shows.
Will Beta work on a hybrid model with hydrogen and electric to extend range?
Yeah, great question. The question was, will we extend range with hybrid systems, hydrogen or obviously recip or turbine? Our philosophy is this, that a hybrid aircraft is an electric aircraft plus a diesel, a hydrogen, or a gasoline aircraft. Plus is the key there. Because in a hybrid aircraft, you still need a battery, an inverter, an electric motor, and all the systems to support that. The addition of hybridization, a generator, a turbo generator, or any other kind of generator, a fuel cell, is in addition to a safe, reliable, repeatedly produced electric airplane to start with. So the strategy is not complicated once you think about it through that lens. It's design and build and certify an electric airplane and add the hybrid. Now, that said, in our labs, we have designed, built, and flown hybrid aircraft as well that simply use all the infrastructure of the electric airplane. But from a certification standpoint, the goal is to get the simplicity down to the maximum level possible and then add back things that add range or functions or features. But from a commercial perspective, it's not necessary right now. When we have a slippery airplane that envelopes the commercial needs of the UPSs and others, then why would we add the cost and expense of an additional hybrid engine until we built enough aircraft to satisfy that market, and then the need is to go longer range. So yes is the answer to the question, not today, for both technical and commercial reasons.
How has G3
We got real-time questions that people who decide to show up, right? We got a glider pilot. This is going to be a good one.
My question has nothing to do with gliders, but you mentioned you use the prop for, I guess, drag or braking. Is there a concept of regenerative braking on an aircraft? Meaning
Yeah.
energy back in the back?
Yeah, he's just a pilot. We'll give him a break. It is regenerative. So the prop, not 100% efficient, not even quite as efficient as making the propulsion. While it spins backwards, it doesn't go backwards, but the torque is reversed, so it goes back into the battery. So for example, if you push it up and you're putting out 300 horsepower, you may be able to come down the glide slope and put 50 horsepower back into the battery. So you'll see the voltage come back up. It's a good question.
I was curious if there was a decision between fast recharging or even swapping the battery out.
A great question. So the question was, did we consider swapping the battery versus fast recharging? And I think as we're all airplane people will empathize with the fact certain things are pilot allowed maintenance and certain things are AMP and allowed maintenance. And this sits in a gray area. We don't want to operate in gray areas, right? We need clarity. That's one. So we don't want to have to call an AMP to swap all the batteries out, for one thing. The second thing is that to take 2,800 pounds of batteries out, the robotics, the lifts, all that kind of stuff, would probably take you at least 15 minutes to take them out and 15 minutes on a good day when it's nice and sunny and you're on a flat surface. But if the rain's coming in sideways and the snow is blowing and whatever else has happened, sand, you're like, I don't really want to take a 800 volt battery out or put it back in right now that weighs 2,800 pounds. And the charging is remarkably fast. So after a normal mission, it's going to be 20-30 minutes to recharge, which is about the same amount of time to take the packages out and put them back in, or take the people out, put them back in and get relaunched. After a full mission, it may take 45 to 50 minutes, and that's after you've kind of run the thing way down to the top of your reserves. So when you do all that, you say, geez, it really doesn't make a bunch of sense to take the batteries in and out and in and out. Yes, sir.
Battery cell advancements, whether it's solid state or drop-in anodes, are you looking at all of the above and the pitfalls? And there's a lot to
Yeah,
this.
this is a great question. So the question is the battery cell advancements, the most important parameter being energy density, other important parameters being cycle life and power density, and cost, of course. So we took control of an old Energizer battery facility in Vermont. and it's about 150,000 square feet. And it is a battery research and development facility where we have hundreds of different cyclers running tons of different types of batteries through all the tests to qualify them. So we have really good visibility in 2, 3, and 5 years what we're going to put in this. But the battery that's in there, that's a 4.5 amp hour cell today. Later this year, a 5 amp hour cell. We already have 7 amp hour cells in our hands that has been fully qualified for thermal runaway, cycle life, thermal mitigation during charge, all those types of things. So my point is that we have good visibility on batteries 3 to 5 years in front of us because they're already in our lab. They are sodium based, they're high silica based, there are pouch, prismatic, and cylindrical cells for different reasons with different chemistries, and we're getting very high energy densities in some of them and really low cycle lives. So we got to trade all these different things to figure out what the next cell you put in is. But our plan is we sell that airplane, and then over the course of the 35,000 hours, it's a working aircraft, meant to work every day, 35,000 hours, the customer will get an increasing amount of battery energy density. They can trade for more range or put 4 instead of 5 batteries in and get more payload.
Thank you.
What does maintenance look like?
Great question, Sheridan. What does maintenance look like? So I mentioned before, the engines are pretty amazing. They don't get hot, they make no corrosive gases, no metal touches any other metal, there's no lubricants like oils and stuff. There are bearings in there that are permanently sealed grease bearings. So there's really nothing that goes wrong in the engine. In fact, I can't say nothing goes wrong. The probability of something goes wrong is very, very low because nothing's getting hot and there's no corrosive gases and all that type of stuff, right? So the maintenance is really, really low, or so we've shown with all of our different flight testing. Same thing, bell cranks, pulleys, no hydraulics. So none of those systems exist. Everything is solid state, which lasts significantly longer. So what we've found, and Chris can speak to this on the road in real time, is significantly less maintenance. What did you guys do in the cross-country flights?
So this aircraft right here has almost 18,000 nautical miles under its belt. It's got 275 flight hours, probably about 500 plus landings and touch and goes. And so far what we've had to do to it, other than just normal inspections, we did a normal 100-hour inspection on it, are change the 2 main tires and brake pads. That's it. And this aircraft actually started out as a cargo aircraft where we obviously modified it to a passenger aircraft. So there was some, extensive cutting into the side of the aircraft that Ed Hull and the industrial design team did and made a beautiful passenger plane. But from a operational perspective, it's making sure you got air in the tires and the brake pads are good to go. It works.
Yes, sir.
So for the VTOL version, do you get the same benefits of the wing for if you lost all power, for example, or you can just glide in? Is it going to be similar or close to it?
Yeah, it's a great question. The question is, in the VTOL, do you get similar performance on gliding?
Yeah.
So, interestingly enough, the FAA, they published their advisory circular for powered lift aircraft last week, and there's a press conference this week, I think on Thursday, about it. It's a huge step for our industry. Not only is this thing a great glider as a CTOL, it's a pretty darn good glider as a VTOL. It's still better than most planes that you would have flown, turbine planes or otherwise, as a VTOL gliding. And so if you were to have a propulsion failure or something, even in the VTOL, you're a remarkably good glider after that failure. So the answer is yes. Should we wrap it up? Everybody looks like they're hungry for lunch.
One more quick one.
Oh,
So I know as a company you're doing the commercial stuff, but you're talking about general aviation, learn to fly as a general aviation pilot. Is there any stuff down the road where a guy looking at a caravan to load his buddies up will look at this instead?
I hope so. Yeah, the
Okay.
question was we're starting with commercial, and the reason is we're introducing a new technology. There's a big appetite for the low-cost, high-cadence operations, right? Big benefit when you take the recurring cost of fuel. One of the things, this particular plane, I flew from East Hampton to JFK to thread into the jet traffic, carried a bunch of passengers on it. It was awesome. But the cost to fill the electrons back up in the battery was $7, right? Now, you still got not a cheap airplane. You got to pay the landing fees, you got to pay the pilot, the insurance, all that stuff. So it's not that ratio of total cost, but it's a big chunk. It's about 42% less cost. Now, that informs what type of flying you want to do that with that. If you have a low recurring cost of operation, you do something like Carol Tomey, the CEO of UPS, said to me. She said, you want to sweat the asset. Once you own it, just use it as much as possible. That's not how general aviation pilots fly, right? You're not out flying 6 flights in a day. Training, maybe. But generally, that's not where a guy buys a caravan or a gal buys a caravan. Is like, I'm going to take my buddies once a month up to camp. So it's not the perfect airplane for the once a week flyer, just because you don't exploit the benefits of it, unless you really want a sustainable aircraft. It's a good question. One more for the glider pilot, then we're going to call it a wrap.
Yeah, I know for any eVTOL or any electric vehicle, I know thermal event propagation is a big risk. And obviously in a car, usually you have a few minutes to get out. I guess what additional
Yeah, great question. The question was, from a battery safety perspective, what mitigation do we have from thermal propagation, or thermal runaway, as we say in the industry? So those batteries in there are 5 packs that are at full voltage. Inside each of those packs are 11 modules. Each of those modules about 60 volts. In that 60 volt block, it's in a titanium tube. That titanium tube has a vent manifold that goes out the other side of the airplane. You can see that there. That's the last line of defense. The first line of defense is an acute awareness of what's going on the battery. So we have a battery balancing and management system that looks at the voltage at every one of the 196 layers of cells. So about 4.1 down to 3.8 volts, right? And it's looking at that compared to every other cell in the pack. As you move current in and out of it, how does it behave? The cool thing is batteries generally tell you, if you ask the right question, hey, I'm getting a little weak. Hey, next week I'm gonna do something you don't like. You might want to do something about it. And then like an hour before, it's like, hey, you're gonna want to land, buddy. You just got to ask the right question. And you look at the internal resistance, you look at the temperature, you look at that difference of charge retainment within the different layers. These are all things first principle physics tell you this. So acute awareness. And then the cells themselves, something called passive propagation resistance. You separate them, and if one cell gets hot, you just keep it from propagating to the next, right? Now, if it does propagate to the next, we actually have to prove that no matter any combination of cell failures, you still, 5 packs, remember, all isolated from each other, you still have to vent that out, land safely, and walk away from the airplane. So you only lose 20% of your energy in one of those failure scenarios. So it's like, you hear belt and suspenders. We have a saying, it's belt and suspenders and we wear underwear. So we've got layer upon layer of safety, and it's at an extremely high bar, and the amount of testing necessary to show this is astronomical. I'm probably not supposed to share this, but just last year, I was just looking at the budgets. We burned up $6 million of battery cells, burned them up intentionally to show that if cell 1A and 3B and cell 2F and 1C light off at the same time, all these different permutations of failures, and the thing is still safe. It's actually a pretty remarkable amount of testing, and it's because it's new and novel, and our FAA has set such a high safety standard, and there's a reason that it is the gold standard in the world, and we have to comply to that. So yeah, it's something that we're really passionate about, and we've taken a lot of time to understand, but it's a good question.
That's a great answer.
Awesome. Anything?
How high
No?
can it fly and how many passengers?
Well, high can it fly? 14 and a half.
How many passengers?
6 people. I find myself a pilot passenger, so I don't know how to count myself.